Okay, so this one's going to be a complex problem, but it's also going to be geared around specifically the AP level. So we don't ask our Gen students to solve any of this, although most of the complex ones we don't really ask them to do too much with. But this is specifically for AP, and I'm going to use some of the terminology and the types of things that you'd be asked to do on the AP Physics 1 exam and the AP C exam. So if you're preparing for the AP exams, this is something that shows up on some of the free responses for both of them. So here's what we're going to do. In fact, I can set my calculator down because most likely I'm not going to need it. Here's the problem. We got a huge sign that a police officer is hiding behind. And then a car who is mercilessly speeding goes flying past at some speed, a constant speed of Vs. Now, here's the other thing. We're going to solve this problem, and I am not going to give you a single number, aside from maybe a couple of values that are 0, but no numbers. So that's going to be another thing. In fact, I'll go ahead and bring this up right now. I'll read it in just a moment. The key to this is you will see the word derive on the AP instructions. So derive usually means that you're going to be working mathematically with equations, but you won't actually be working with numbers. Okay. So the speeding car, Vs, goes with some speed of Vs the entire time, not speeding up or slowing down. Okay, they see a speeding car go by. The moment the speeding car drives past the police car, the officer presses the gas and starts accelerating. Let's see, and they accelerate at a sub p, the acceleration of the police officer, until they catch the red car. So we're not going to worry about any top speed for the police car. It's just going to start from sitting there, because its initial velocity, the initial velocity of the police officer was 0, and then some final velocity, however fast it's going when it catches the red car. But we're not going to worry about, in real life, you'd probably have the police officer speed up to however fast they need to go and then try and run down the other person. We're just going to say that they accelerate uniformly at a sub p the entire time. Okay, here's what we've got. Derive an expression for the time it takes for the police officer to catch the speeding car in terms of Vs, a sub p, and constants. They usually have something in there about any universal constants. That'll be things like the acceleration due to gravity or the density of water or something like that. They provide that on the AP equation sheet. Some of the ones you see later on, you'll need to have things like the acceleration due to gravity in there or something like that. We don't actually have that in this problem, so I just have it in there because it looks kind of like what normally comes up. Okay, so we're going to get an answer that has Vs in it or AP in it or both, but it can't have any other variables in it, and we're going to see how we work with that. So we need to derive an expression for the time it takes for the police officer to catch the speeding car in those terms. So let's start with that. Much like we've done before, we've got two objects, so here's what I'm going to do. Delta x of the police car. We've got v final of the police car, which we don't know, and presumably don't care about, we're not asked about it. Our initial velocity of the police car is actually 0. That is technically a number, so we are working with some numbers. Usually the only number you work with is 0. Or sometimes you'll be given one thing in terms of another. The acceleration of the police officer, which is a sub p, and the time, which is actually the thing that we are directly looking for in the first part. We've also got the motion of the speeding car, which I'm going to call their displacement, delta xs. Their final velocity is vs. Their initial velocity is vs, because they're going at a constant speed. And the acceleration of the speeding car is going to be 0, because it doesn't speed up or slow down. We also have a time. Now, I didn't mark the times individually because they both start right here as the red car goes driving past, and they will end when the blue car catches up to the red car sometime later back over here. They will both have the same time that they are traveling with. That's something to bring up. Take a look at some of my previous videos, because I had at least one or two where the times are not necessarily the same. I might ask this question in a way where the police officer, it takes them 10 seconds to respond. So they have to wait 10 seconds, then they start accelerating, and the times would not be the same. Something to think about. We also have, they're both going to go from the large sign where the motion begins until the speeding motorist gets caught over here. They both are going to go the same delta x. That makes this a little bit easier. So our delta x's are the same and our times are the same. So from here on in, I'm just going to refer to them as delta x and time. Now that by itself, we still have two unknowns, so we got to play around with them. We're going to need some more equations. And like you've hopefully seen in some of the other videos, please check those out, we can go through and we can actually try and put that together. We want our displacement and our times in there. And with this, since we don't care about and don't want, and don't have, I should say, the final velocity of the police car, let's use the equation that doesn't have final velocity. So we're going to use the common one, which is this, plus 1/2 AT squared. For our police officer, we see that we get delta x of the police officer, but it's actually of both of them, equals our initial velocity, which is 0 for the police officer, times our time, plus 1/2 a sub p t squared. Now this is 0, so it disappears into a puff of nothingness, and we get one equation that we need, which is delta x, our displacement, is equal to 1/2 ap t squared. We can also look at the speeding motorist using the same equation. Delta x equals our initial velocity, which is vs times time, plus 1/2 at squared, but the acceleration of the speeding motorist is 0, so that one disappears into a puff of nothingness, and we get another one of the equations that we need, delta, oops, I was writing them in black, delta x equals vs times time. Now, this one, because there's no acceleration, distance equals rate times time. But this one does not come up with that because it has an acceleration. I'll warn you, be very, very careful using distance equals rate times time or velocity equals distance divided by time. Those only give you the right answer if there is no acceleration. They will not give you the right answer for the police officer. Use the kinematic equations that we have for solving that. Okay, great. Both of these, delta x is the same and t is the same, so I can do what we did before. I can set these equal to each other. Cut out the middleman. So I get 1/2 ap t squared, which is delta x. It will also be equal to delta x, which is vs times t. I can divide both sides by t. One of these cancels out, and the squared cancels out. And I want to get the following. I'm trying to solve time. So I'm done when I have time equals some stuff. And that stuff can only be in terms of vs and ap. That's that, get it in terms of something. Well, if I solve for t here, I get that time is equal to, I divide by ap and multiply by 2vs over ap. There you go. This is the time it takes for the police car to catch the speeding car in terms of the speed of the speeding car and the acceleration of the police officer. At this point, we've actually solved every single one of these problems that matches that. We could say, oh, the speeding car was going 40 miles per hour, and the police officer accelerates at 3 meters per second squared. Or we could have a different car that's going 80 miles per hour and have a different acceleration for the police officer. What we've done here is we've solved every single problem. All we need now are the numbers to put in there, and we don't have to redo any of it. We have now solved every single problem that matches this. That's the upside of doing this derived stuff. I know most people hate it when they first start working with it, but if you want to go into things like physics, we actually get more and more training, and this is how we solve all problems, so we don't have to worry about making a mathematical error and having to redo the whole thing. That's another upside. Part B, derive an expression for how far the police officer is from the large sign when the speeding car is caught in terms of the same values. Now I'm asking for delta x. We could find delta x for either of them. So let's take a look at this. I'm going to go back to what we had looked at before. We had delta x equals 1/2 ap t squared, and we also had that delta x was equal to vs times t. Okay, this time I want to solve for delta x instead, so there's something else that I can do. I can pray that my board starts working. I'm going to move these around a little bit. I'm going to solve for t instead. So I'm going to say up here that t is equal to, I multiply by 2, so I'd end up with 2 times delta x divided by AP, that would be t squared. So I'm going to take the square root. Great. And then over here, I can find that t is equal to, let's see, delta x divided by vs. Now that I've got this, I can actually set these two equal to each other. So I can do the following. Square root of 2 delta x divided by AP is equal to delta x divided by vs. Both of these are equal to my time. I really don't know why it's doing this. You've not done this for 6 years. Why start now? All right, mental note, check drivers. Okay, now that we've got this, what we want is delta x equals some stuff. We're most of the way there because I can see immediately the only things in my problem are delta x, which is what I want, delta x equals some stuff, and AP, which is allowed, and vs, which is also allowed, and 2, which is just a number, so it's allowed. So at this point, I've got to do some algebra, which kind of sucks, but it is what it is. So to clean this up a little bit, I'm going to square both sides. That gives me 2 delta x divided by AP is equal to delta x squared over vs squared. Great. Now I got rid of that square root because that's always a pain to try and work with stuff with. I want delta x by itself, so I can divide both sides by delta x. 1 over delta x, 1 over delta x. What does that give me? It cancels this one out and cancels out the squared. And I end up with the following. That we end up with delta x divided by vs squared. I'm going to finish doing some algebra here, multiply both sides by vs squared. I guess I could have done that here. Vs squared, vs squared. And we end up with the following. 2 times vs squared divided by AP equals delta x. Here's our answer for this one. Now there's one thing that I skipped over in the first part. I'm going to bring this up. These are all still physics equations, which means while I got lazy with units in some of my problems, hopefully I'm able to actually find where I'm going. Thank you. Great. Great. There's the other one. You can check to see if you've made a huge error, if your equation can actually work or not by checking the units. So we've got the following. This is a velocity, so that means that we would have meters per second. 2 doesn't have any units, at least that they've told us. And our acceleration is in meters per second squared. So that's what I came up with. My meters cancel out, my seconds cancels out with one of them, and I've got 1 over seconds in the denominator. Well, I could multiply that by seconds over 1, but I have to do the same thing up top. That actually becomes seconds, so all of this has units of seconds, which is what I expect for time. Let's see what we get down here with this equation. So I've got delta x, which should have units of meters. Here I've got v squared, so that would be meter per second quantity squared, so that's meter squared per second squared up top, divided by meter per second squared for the acceleration on bottom. Well, they're both divided by seconds squared, so that cancels out, and the meter cancels out with one of those, and we're left with this has units of meters as well. The units must work out. So that's a great way to check if you've made a mistake or not. Won't tell you that you're completely correct, but if your units don't work out, you've definitely made a mistake because it can't possibly be a real equation. But these, so far as I know, look like they're what they should be. Here is our solution to part 2. Delta x in terms of vs and AP. And technically constants, 2 is a constant. T, our time, in terms of vs and AP. Now the last thing that I've got on this one, and this is common on the AP1 exam. APC, you're going to have to do a whole bunch of this, but AP1, they like to follow it up with something else. Another student working on this problem derives an equation for the time it takes for the police officer to catch any speeding car as a function of how fast the speeding car is going, v. So what they're saying is time as a function of v, where v is how fast the speeding car is going. Okay, and they say that it equals some stuff. They give us the following. Our time is equal to a divided by v, where v is how fast the speeding car is going, plus b. And they say the following, that a and b are constants with appropriate units. Now I showed you that we just check the units, But whenever they say these have appropriate units, it means that they have whatever units they need to make the whole thing work out. So your answer is never that the units don't make sense. Do not write that. I have a bunch of students who keep writing that. I don't know for certain if that will ever happen on the AP exam, but all the questions I've seen up to this point, the correct answer is never the units don't work out right, so it's not a real equation. Ignore the units, especially now they've started saying it has constants with appropriate units. These have whatever units you need to make all the units work out. What they're actually asking you about is to understand what happens. These are just numbers, they don't change. It's saying, there's something wrong with this equation, tell us what it is. And to do that, you have to think about what this actually represents. This is how long it takes for the police officer to catch the other car. Okay, what if the other car is going real slow? If we have a very low value for V. Let's say that this is 10. 10 divided by 1 is 10 plus some number, so we've got 10-ish. As V gets small, that means that A stays bigger. We end up with a bigger value for time. But if V gets really big, if V goes to 100, 10 divided by 100, this becomes 0.1. Plus, let's go with, let's see, so small, let's say that V is really small and A is 10, so we would end up with 10. Plus, let's just say that B was 5. So B is always 5. A is 10 divided by whatever V is. So for the red, V is 1, a small number. But for blue, V is 100. That's describing how fast the car is going. So if the velocity of the car is the red one, that's 1 mile per hour. It's barely moving, right? How long is it going to take the police officer to catch that car? Like, not very long at all, because it's barely moving. But let's see what that means. If V is small, then that means A is going to stay big, and we end up with this equation says that it will take, 15 seconds. But when the speeding car is going very fast, our big value, blue, 100, 10 divided by 100 is 0.1. That says when the speeding car is going very big, this is a big value, and this gets small, so we have a very small number, 0.1. This would be 5.1 seconds. Does that make sense? If the speeding car is going 1 mile per hour, it's going to take 15 seconds to catch it, but if it's going 100 miles per hour, it'll only take 5? That's actually what this question is asking. And you have to ask yourself what these variables represent and what happens mathematically when we change them. Here's the problem with this student's equation. When the speeding car is going very slow, the police officer takes a long time to catch them. But that doesn't make any sense. And when the speeding car is going very quickly, it takes a very short amount of time for the officer to catch them. That also doesn't make sense. In other words, what we would expect to happen in real life doesn't agree with this equation, and that's why it doesn't make any physical sense. In order to answer these questions about what's wrong with the equation, you have to look at what's changing and what it predicts with your outcome and see what happens. All right, these take some practice, but it's one way to look at them.